So, welcome everyone. We're going to cover a couple more aspects of the crystallinity, crystalline planes, what it means, and why it matters. Each of these examples from cubic we've talked about, and we went into a fair bit of detail. There's a number of other types of crystalline lattice arrangements, and I wanted to make sure that we had covered some of those. So there's a few more pieces to the puzzle here that I think are going to be very, very important. So um, the cubic structures all have alpha, beta, and gamma. What these are referring to is they're referring to the angle from one plane to another. So in this case, they're all 90 degrees. In the case of tetragonal, they're also 90 degrees. In the case of orthorhombic, again, 90 degrees. In the case of hexagonal, um, they are, each of these is, it's 90 degrees here in this plane, but it's 120 degrees on the base there. So it's a little bit unusual. Trigonal is a little bit different. It's at a slight angle. And this is when you start getting into especially things like monoclinic and triclinic, there can be a tendency to think, well, gee, man, like all this nonsense looks the same. Like, what are you talking about? I don't understand. In this case, it's these angles that are 90 degrees, and it's these angles that are different. So beta is not 120 degrees. So the angle matters, and how far that goes matters. So we'll talk a little bit about this. This is I'm going to clarify on the I'm going to clarify on the hexagonal. The top is 90 degrees. These angles tend to be about the identity angle with 120 degrees. This angle tends to be actually 120. So we'll talk a little bit more about that. But I wanted you guys to at least see a few of these. So none of these sides are equal. None of the angles equal 90 in the triclinic. So this is triclinic and trigonal are kind of the two that catch a lot of the other scenarios. So alpha and gamma are 90, alpha and beta are 90 in the hexagonal. So this just gives you a couple of ideas. So there's four types. There's the primitive, there's the I, which is body-centered. So even though these are body-centered, these are not body-centered cubic. These are orthorhombic or tetragonal. Face-centered is the F, and the C is side-centered. So all of the atoms have side interactions. These are just meant to give you an idea. So there's a bunch of different total lattice types, and we want you to at least be familiar with them. We're not expecting you to know all of the angles off the top of your head or anything ridiculous and silly like that, but we want you guys to at least have some sort of a concept. Another thing that can happen as we're going through these materials in these chapters is you can start to have some issues with this all sounds great in theory, but like this could all just be a bunch of made up nonsense and I wouldn't know the difference. So here's an example of an iron carbide lattice on the left and what that looks like. So you have a couple different things that are going on all at the same time. You'll see some fairly well focused images on these microscopic images. So those are ones down below. At the top here, what we've got is a couple images of the actual carbide. So they're showing where the ferrite boundary is, and they show a couple of different lattice parameters here that line up. So sometimes you'll have 2, 3, or 4 different lattices that will show up in a spectrum on a material just because of the way that different specific grains are oriented and things like that. So there's a boundary that they're looking at specifically here with a couple specific planes. So here's another example of carbon in the middle of what would otherwise be simply face-centered cubic arrangement, but it's helping to highlight what the interaction actually is in the center. So this is austenite, which is the gamma iron. So this is the very, very strong form of iron when you have enough carbon present that actually allows you to see these stripes. These are these austenitic grains, these gamma grains. This is another image of what that crystalline lattice actually looks like. So it's pretty helpful to be able to see it in another context. Another thing that I thought would help that I came across was if we were labeling these and think about it in like the perspective of SolidWorks, and you have a front view, a right view, a top view. You've also got you've got a couple different views that are taking into account all three. There's an isochoric. There's a couple others that will help to kind of set the view and make a little bit more sense of things. But this is the 100 plane. So this is the top plane. This plane is actually the 110 plane. This would be the 111. This side, for instance, would be 0, 1, 0. This top one would be 0, 0, 1. And that's why the families of planes are similar. This one along the side, this would be going the opposite direction of this one. So it would be instead of a 110, it would be a 1, -1, 0. So 1, 1 bar, 0 would be this back plane, for instance. So thinking of each of the crystalline lattice planes based on a cube like this that you can more easily visualize in SolidWorks is part of the reason why I did that demo with you guys, was to get you guys to sort of start understanding what that looks like. So here are a couple really high resolution scanning tunneling microscope images to be able to see what the actual lattice parameters are doing. And what the 111 arrangement does is it literally creates those triangular forms with the atoms, and it becomes very easy to see. So this is a graphene iridium. I think this is a graphene. This one might be a graphene rhodium. This one I think is graphene nickel, and this one I think is graphene rubidium, something like that. But it actually does form into triangular orientations because of the lattice parameters at the macroscope or at the microscopic level for the individual layers and levels. It's helpful to just sort of see some of these. So taking that sort of cube and the view perspective a little bit further, you can see some examples. So this is that 001 top plane. You have a 010 at the front here. You have a 110 at the front here. You have a 111 that's going diagonally, and you have your 110 that goes across. So this is the 11100 is this front plane. The 110 is going diagonally back here. And this gives you some sort of idea about what the relationships are. Hexagonal, hexagonal is a little more difficult to envision, but this image I think is actually very, very good at summing this up. So the 0001 is this top plane. You have 1, -20. So 1 in, so A1, 1, A2, 1, A3, -2, and then 0, meaning all along this C axis. So anyone that's going infinitely along the C axis is going to have a 0 there. So that's why all of these examples do. So 2, -1, -1, 0 is another one that's given here. Another plane that is 1, 0, -1, 0 is infinite along A2, hence the 0, and infinite along C, hence the 0. So there's a couple kind of quick sanity checks that you can think of is wherever the zeros are, it needs to be infinite in that general direction for these lattice parameters. So this is, I think, one that'll help clarify some examples, since hexagonal can be a little difficult to visualize. It's actually a very sensible coordinate system, but it's not something that we use very often. A couple other definitional things. I'm 100% certain that you guys are not fully clear on polymorphism, and the book does describe it, but I thought I would spend some time on altering the way that we think about those definitions so that they can be more clear. So polymorphism is what happens when a substance can crystallize into more than one type of crystalline structure that are the same chemical composition but different atomic arrangements. Each unique arrangement is itself called a polymorph. So I don't want you guys to be super confused on this. The external conditions like temperature and pressure, using the principles that we just learned last week about grain arrangement and behaviors. Presence of impurities we're going to learn about as we get into chapter 4, because I want to go ahead and include chapter 4 before we go to do some of the next testing, because after 4 we begin to shift our focus. So I want to get through 4 this week. Then we'll do exam things. Because 4 really goes with this whole topic, and it really can't be separated out. Not and make sense. So those external pressures, temperatures, and presence of impurities change the atomic arrangements within the solid. So different polymorphs are going to be stable under different conditions, at different pressures and temperatures. There are a couple different types. So an anisotropic is one that we're not going to spend a whole lot of time on these, but you just need to know that they exist. Enantiotropic are similar in chemistry to enantiomers, things that you haven't really had exposure to because they are speaking toward chirality and arrangement of atoms in a molecule, whether or not they are reversible, whether or not that changes their physical and chemical properties. But they're something that are able to transition back and forth between two different crystalline structures depending on the condition. And monotropic is one polymorph stable under all conditions, all times, and the transformation from one to another is irreversible. So those are important distinctions, but we're not going to focus too much more on those. Iron is a very good example, and this is part of the reason why we're going to spend most of the time on the iron phase diagram, and that's all stuff that we need to get to because that takes, like, just the iron phase diagram is effectively an entire day all by itself of lecture to really comprehend what is there. There is so much information in the phase diagram, it's ridiculous. That's why they say a picture is worth 1,000 words. You'll find out soon. So alpha iron is ferrite, body-centered cubic, stable below about 912C. Between 912 and 1394 is gamma iron. So that's the crystal structures that we just looked at. That's FCC. So austenite is what that's called. Each of the forms of these materials have a unique name, and there's probably not very many people who know all the names of all the crystals of all the different materials because there's like 35 million cataloged compounds or more. Maybe there's closer to 50 now. I don't know. There's a lot. So that face-centered cubic structure is only stable in that region. Then there's delta iron above 1394C, right? And it's another BCC structure, and it's mostly because of the kinetic energy. There is so much heat trying to be contained and managed by those individual molecules that it's very hard for it to not expand to the less space efficient BCC at those temperatures, just because all that kinetic energy has to be stored somewhere. And the actual physical sort of growing of the material, that process at that high temperature is done by a rearrangement to body-centered cubic because it has so much thermal energy to store that it can afford to change its spatial efficiency away from FCC. And that's part of what makes this all interesting. So alpha iron is ferromagnetic. You are familiar with this form of iron because it's very common for cast irons to be in the alpha iron form. The material can't be magnetized in gamma iron, which is paramagnetic. So this changes some of the production processes, such as heat treatment, and part of the you can't really heat magnets. When you do, they have all sorts of deleterious effects. So alpha iron is pretty important. Titanium is another good example of this. A hexagonal close packed structure that's stable at low temperatures, whereas the beta is body-centered cubic, stable at higher temperatures. So again, same kind of idea. It's got to store all of that kinetic energy somewhere, and that often comes in the form of less space efficient materials so that the molecules have more room to physically vibrate at these higher frequencies because of that higher kinetic energy. That transition affects the mechanical properties. So alpha titanium is strong but less ductile. Beta titanium is ductile and easier to work with in manufacturing. I believe the forms of recent, like the titanium frames on recent iPhones, I believe they're working with a beta form, typically, to actually make them. So it's supposed to be a very strong frame, except it ends up being more ductile physically. So it's easier to physically bend, and therefore do things like break the back glass or crack the screen on these titanium framed iPhones. Even though we think of titanium as being this super duper strong alloy, typically it's yes, but also no. So there's that. Silicon dioxide is another one that has several polymorphic forms. Quartz, cristobalite, and tridymite are common forms. So quartz being the most common form at room temperature. Cristobalite can be found at higher temperatures. And tridymite is one that probably you guys won't encounter a whole lot. So we don't need to worry about what the names there mean or what specific form they have. But in things like geology and in construction of ceramics, but most importantly in the development of electronics, where you need specific piezoelectric properties or something like that, you need to have careful control of the quartz, because they will, especially as they have a voltage applied across them, the quartz crystals will vibrate at a certain frequency, and that frequency is dependent on how those crystals are grown. So they have to be very pure in order to be highly accurate. So it used to be a big deal to say, oh, well, my watch uses quartz, which is a thing that you guys will like never hear in your entire lifetime. Because the idea of a digital watch that used quartz to keep more accurate time was kind of a big deal. So now people don't care because phones do everything. Carbon and diamond is another good example, going back and forth. So the diamond has a cubic crystal structure that is tetrahedrally bonded to 4 other carbon atoms. So the hardness is very, very high and transparent. There's a transparency there. Graphite is structured where the carbon atoms are bonded to 3 others instead of 4 in a hexagonal plane, and so the weak van der Waals forces between the layers make graphite very soft, and it's great for conducting electricity because of those long flat sheets where electrons can sort of zip across the surface with relatively low impedance, even though it's carbon, and we use carbon in resistors, and don't ask questions you're not ready for the answer for. The allotropy versus polymorphism, this is another one that I want to make sure you guys understand, is the allotropy is a very specific case of a polymorphism, such as something like carbon or iron. It's a very unique case. We're going to look at some more definitional aspects here in just a second. But a polymorphism can be in any material, any kind of element, titanium, silicon dioxide, polymorphisms, but they cannot be allotropes because an allotrope requires it to be a single element, which is why graphene and graphite and diamond would all be in that same category. So the polymorphism allows multiple of these different crystal structures to exist at the same time. And it's something that happens in metals, minerals, and even pharmaceuticals that affect a lot of these different properties and therefore how they can be used in the end use. But the allotropy is fairly unique. There was one more thing that I thought I would include here. It's going to be uh, quite a bit blurrier than what I would like, but since we don't actually have the Star Trek enhance thing, um, then yeah, we can't actually just do like what they do in movies and uh, improve the resolution of things. Chop chop. Um, the slip planes, we're going to learn, especially in terms of defect and fault propagation. We're going to learn some more about that and how that ties in with the chapter 4 materials. Um, the slip planes are important to understand because depending on how the atoms are arranged, for something like FCC, um, there will be a 111 slip plane. For BCC, there will be 110, there will be a 211, and there will be a 311, because each of those are related to each other. So an example they give is something like in alpha iron, there will be those slip planes. But notice how many slip systems there are. Um, the the slip systems are doubled in the case of the 311 plane, um, compared to the 211. So uh, there's a lot of reason why the BCC arrangement of atoms is more malleable. It is more ductile. So it is more easily moved and bent and reshaped under force than an FCC is. FCC also, because of those slip planes, when you're trying to remove material from a bulk, the FCC arrangement is also going to make it easier for uh, those materials to be very, very sharp. So there's a reason why a thin plate of a thin foil or something like that of copper or aluminum, or silver, uh, there's a reason why those kinds of materials can actually be very wicked at giving what we would otherwise call paper cuts. But it's actually because of the jagged serrations that are going to show up at the edges of those materials because of the 111 slip plane orientation of those kinds of materials. So these actually can make for very effective cutting edges as a result. And anybody that's had a quote paper cut from a metal foil, I'm sure can testify to that. So I think that was the ones that I wanted to cover. Yeah, that was the ones that I wanted to cover from this. Um, I'm going to switch over and grab chapter 4 materials. Just because that's going to kind of continue some of what we've started to apply here, but it's going to take a couple more steps. So while I'm pulling that up, any questions that you guys have, like, hey, I'm still super unclear on that, or +1 if this is generally helped fill in what you felt like were a couple of gaps. All right, here we go. So you've gotten a little bit of a precursor. I don't see any major questions coming up. So I'm going to go ahead and share this. Okay. All right. So we're going to cover what we can here for chapter 4. There's a few things that are going to be key to this, and it's going to take time to understand how they apply. But because we've covered some of the end applications, it'll start to make a little bit more sense and why we need to go ahead and get into this instead of stopping doing any additional review. So solidification is very, very important for molten material, especially because a lot of times it's easier to start with a liquid and cast something because you can make a specific shape and it doesn't require zillions of hours of machining time and all sorts of other things. So as a processing mechanism, liquefaction and then solidification is preferable because it can allow you some lower cost manufacturing. There's a couple things that happen in this. You start with nuclei forming. So we saw examples of that in the film from the ancient British example there, but you got to see the crystals actually grow and form on that film from the nuclei. So the nuclei form, the crystals grow until they reach the boundaries of another crystal, and then they stop. So the material comes out of liquid into solid in that manner, and that boundary between the different nuclei growing together, that boundary is called the grain boundary. The grain structures are what are left. So their example was, you can see at the macro scale grains of zinc on a galvanized material that are very, very large and obvious. And so it's something worth kind of going back and studying because it's kind of an interesting phenomenon. So you start with a liquid, you start with nuclei, and then the molten material, the crystals grow out of the liquid, and then you end up with the grain structures as we understand it. So this is helpful to see all of the pieces, but it's more helpful to see some of like the video examples that we used already. A thing that's important to understand about polycrystalline materials is the grain boundaries have different angles of incidence, meaning how far misaligned they are. So there can be very small angle grain boundaries. There can be high angle grain boundaries, and those are going to have different levels of void or open space in between them. So the high angle is very likely to have the high angle may actually have less open space than the small angle. It's going to depend on what the specific angles are that you're comparing. So these regions are transitioning from the lattice of one to another, and there's going to be disorder at that boundary always. There's going to be low density in that grain boundary area. And what that means is high mobility, high diffusivity, and high chemical reactivity. Those things ought to make sense because it's easy for a grain to shift relative to another grain and rotate or move slightly compared to the structure that's well defined within the grain. It's not just going to rotate inside of itself just for funsies, right? Like there's actually going to be a reason behind that. So there's a high diffusivity, meaning that especially smaller atoms. So let's say that iron and carbon example, the carbon is going to more easily be able to bounce around through those spaces and weave its way in between the grains, compared to if it were trying to just shove the atoms out of the way in the already defined crystalline lattice internal to an existing grain. The high chemical reactivity makes sense when you think about the difference between a molecule coming in to try and Hulk smash the middle of a grain where everything is nice and rigidly defined. There's a big difference between the amount of energy it takes to try and impact here and create a reaction versus trying to impact here to create a reaction, because there's enough space where another atom or another molecule can come in and hit this edge, hit this grain boundary, and knock loose some of these atoms in order to make its molecular attack. So this is thermodynamically favorable, and that's why grain boundaries are vulnerable to the chemical reactivity. So the solidification looks like this, but in order to understand what that is, I'm going to see if I can pull an example, because it's not going to make sense otherwise. Let's see. Let's see. There's a bunch of examples, but let's take a closer look. Let's see. There's a couple really good ones. Yeah, there's going to be I don't want to walk you through a how to get yourself seriously injured video, because that won't be helpful. But this one I think will be a good example. So let me go ahead and use this. Let's see if I can get through any extras. Yeah, this will help.
Foundry industry, or whether you're try and make a sandcastle as quickly as you can. When you first go on the beach, you're up a long way from where the sea has been, and the sand is very dry. It doesn't really make very good sandcastles because it just pours almost like a liquid. So after a while you run down by the sea where the waves are coming up and you try again, but that sand is too wet and you find that it sticks to the side of the bucket. But between the two sides of the beach, you'll find the sand that's just right, where it's bound together with water so that it will form a perfect sandcastle. They always have a slope on the sides. The reason for that is once you've filled it, you give it the customary couple of pats, that releases the bucket, and then it will lift cleanly off the sand. Rather than using water to bind the sand together, this sand is bound with oil so that it will bind together and hold a shape really well. Using oil means that we can use a finer grade of sand, which will give a better quality of casting. We're going to make our sand mould, in a metal box known as a flask. This is a two-part box which has locating pins so that they can be taken apart and locate accurately each time. The top is known as the cope, the bottom is known as the drag. Today we're going to make two products. The first one is a small cylinder or bearing block, and we'll use sand moulding to produce that. The second product is a small coin, a supermarket trolley, so that you don't have to leave your pound in at the supermarket. To make a simple object, such as this little number plate, it's quite easy to just make it as a one-part pattern which can easily be produced and removed from the sand. It does have sloping sides, it has the draft angle, just like the slope on your sandcastle bucket. Some more complex shapes are difficult to take out of the sand. Even a simple cylinder, once you've buried it in the sand, you wouldn't be able to remove it without breaking the sand, or if you were trying to draw it out vertically, it would break the mould unless you put a taper on it, and then you wouldn't have a cylinder. This can be overcome by splitting the pattern into two parts so that you mould the two parts separately and they locate together using pins in the same way that the pins locate the boxes in the flask. We've already thought about using a split pattern so that you can take the two halves separately. But how can we produce the hole through the middle without having to drill it out? In industry, obviously producing something and having to machine a lot of the metal away is time consuming and cost consuming. So producing it with the hole already in place is an advantage. So we're going to use a pattern. Again, it's a split pattern, but it forms together to produce the outside shape. But it has these locating bosses on the ends, which are known as core prints. They're painted black because that's a visual clue to the people in the foundry that they know they've got to add a core to the mould. So if we take the cope off the top of the flask and set that to one side and turn over the drag, we often refer to that as an inverted drag, and add the first part of the pattern. One side has locating pins, so it sits flat. We'll use the side with the holes face down in the moulding box. This has been set so that nothing touches the sides of the moulding box, and there's a space in the corner for us to complete the moulding work. We give a quick sprinkle of parting powder, and it's just used to help remove the pattern from the sand when we're opening the mould. Because the sand has oil, you may want to wear gloves to protect your hands or use a barrier cream, particularly if you're using reclaimed second-hand sand. We start off by sprinkling the sand, breaking it up as we go, just like making a rhubarb crumble topping. And we partly fill the box. We never fill it in one go. If you fill it in one go, you'll be able to form a very hard surface, but where you need the strength of the mould around the pattern will be compromised. So we just use our fingers to press the sand down to hold the pattern in place. The sand now needs to be rammed down more tightly. This is a typical ramming tool with a flat end on one side and a tapered end to get into corners. I find these are sometimes too large with the small boxes that we're using, so just a piece of broom handle with a tapered end works particularly well. The tapered end is used to get into the corners. You don't need to go crazy. It's not a competition for the world's strongest man. You just add some more layers of sand, build it up. It might make 2 or 3 layers as the sand compresses down. We now need to level off the sand, and that's just done with a piece of bar. The process is traditionally known as strickling. So the tool we use is known as a strickling bar. And if we use a sawing action and take it off a piece at a time, we end up with a nice, flat, firm surface. And turn things back over. And now you can see we've got the pattern surrounded by sand, and we can just run our fingers to make sure that it is firm. That won't do it any harm at all. We now take the second part of the pattern and locate that in place. We add the cope. We have another dusting of parting powder. This time the parting powder serves 2 processes. Firstly, to release the pattern from the sand, and also to stop the 2 layers of sand from sticking. We need to find a way to introduce the metal into the cavity of the mould. We do that by adding a runner. If we were doing a pattern which needed it, or if you were doing an educational course, you would always need to talk about having a riser, which is a second channel on the opposite side. For this particular task, we only need to have a runner. I use this tapered wooden pin, known as a sprue pin, and I place it in the corner of the box. If it touches the pattern, it will damage the outcome. If it touches the flask, the heat from the molten metal will sink out and it will start to solidify before it has completed the task. We repeat the process. Mary Berry would be proud of me doing this. Pressing the sand down and using the ramming tool again to firm the sand. The ramming tool doesn't fit down into the corner, but that doesn't matter. You can use any old thing. I'm using the strickling bar. The sand on the second box, the cope, doesn't need to be quite so firmly rammed as in the drag. We use the strickling bar just trickle off the top the best we can. And then to remove the sprue pin, we just give it a tap, twist it, and because it's tapered, it releases easily out of the sand. I'm going to use a trowel to take the top off around the pouring hole and make sure there's no loose sand, which would wash into the mould. We also produce something called a pouring basin, which makes it easier to pour the metal. It gives you a larger target, but it also reduces the flow rate of the metal going into the mould, so you get less erosion of the sand as you pour. Good practice is to add some vent holes just by pressing in a piece of wire, which allows any air to escape and any small amount of smoke that may be produced by the oil burning out. And we can split the two halves of the flask. The patterns now need to be taken out. That can be done just by giving them a gentle tap and then lifting the pattern cleanly out. We've got a good impression in the sand. The same with the other half. That's come out quite well. There's a little bit of looseness there. Nothing to worry about, that can be repaired by hand. We can see there's a small impression on the sand left by the sprue pin. That gives us a good indication of where we cut the spool bowl. The final piece of moulding work we need to do is to cut a gate. We know what a gate is. It's where you go into something, working away from the mould cavity, and we need to ensure that there is no loose sand. A good way of doing that is to blow, and it's sensible to pop on a pair of goggles to make sure that nothing blows back into your eye. So that is the basic mould produced. We just need to produce the core to lay across so that we can form the hole through the middle of the casting. We use the two-part block, introduce sand, poke it down and ram it to give it some strength. Make sure it's full, trim the top, and then by giving it a tap, it should release the core, which you can carefully lay across the prints. The two halves go together, again just checking for loose sand, locate a pin, put it together, and that's ready for pouring. Because we're going to be using molten metal, we have a bit of health and safety going on. A leather apron saves any splashes to the body, suitable gloves, and finally a full face visor to keep things nice and tidy. So after a break of 5 to 10 minutes, we now have a pot of molten metal. I'll just turn the burner off. Nice long tongs so that I'm well away from the heat. Just rest it, move the tongs down, and then pour the metal into the pouring basin so that it gently flows. The top of the metal is slightly convex when you first pour it, but as things cool down, the casting contracts, the metal will feed in, and we'll see that it becomes concave and dips in the middle of the runner. It may be that you need to provide surplus metal within the mould so that it will keep feeding. You might have to add maybe up to 50% more metal to the mould than you're going to use in your final casting. Okay, so we've let the mould cool down for 10 or 15 minutes. So hopefully, when we open it up, we'll have the magic of a decent casting in there. It's filled well on the bottom part of the mould. Because we've only used a low temperature metal, the sand hasn't really been compromised. We can now break out the casting. It is still hot. You still have to be remembering that it will hurt you if you pick it up. And then we can just take the sand from the core, just poke that out, and there we have the hole right through the casting, and it's come out and quite nicely aligned on the joints. We just have to cut the sprue off, and that can be remelted for the next job. There's very little waste in the foundry industry. So now we're going to look at die casting. This is a nice simple die made out of MDF laser cut to produce the supermarket shopping tokens. It can be produced out of MDF with a laser cutter, channel for the metal to form and the shape of what you're doing. The two slices that go on the outside of the sandwich, one has got text, which has to be in mirror writing, and the other, in this case, has got a little shopping trolley logo, but there are vents to allow the air to escape as the metal runs in. They locate together and have a board backwards and forwards, just so that you've got somewhere to pour the metal. It's held in a machine vise so that it's nice and stable, and we've got a bit of tape around just a secondary clamping so that nothing splays apart when the metal is poured in. And this time it takes quite a steady hand as we're dealing with a fairly small target to pour this metal. And then just to make sure that there aren't any air bubbles, a few gentle taps will hopefully give a good result. Right, so we've given this a few minutes to cool down. I'll just take that little bit off there. And then we can release the tape under the vise and start taking things apart. So I've got 3 parts of the die, and they should peel away. Things are still warm inside, so I'll try not to touch the metal. And you can see that the text has formed nicely. Everything's filled well. On the second half, you can see that we've got a nice clear impression of the shopping trolley. Where the air vents ran, you can just see a very small amount of metal just started to go up, but there's no problem with that on this product. It's just a simple matter of breaking them off the main feed, and then a quick touch with the file or a bit of emery cloth will give it the finish that we're looking for. Okay, so just a couple of last safety things to think about. Don't pick anything up without knowing that it's cool. The burner's switched off, but this setup will probably take 20 minutes to cool down so you can comfortably handle it without safety gloves. Don't go and put it in the back of your car. Don't stand it on a table that will be affected by the heat. Things might not look hot, but they probably are. Make that assumption. So I hope that you've learned something from what we've been looking at today, whether you're watching this as a hobbyist
So that's how we get from the molten state to this kind of crystalline arrangement. So you can see where the material usually flows in from the center. The shell has done what's called, it has equiexed in order to have similar grains as it fills the outside. So it starts cooling immediately at the outside at a uniform rate. Then as you go farther and farther inside, the grains become longer and longer and longer because of that process. The heat takes a lot longer to dissipate from the center, so it takes a lot longer to go from the liquid state to the solidified state, which is why those grains physically grow to be larger in size. The same number of nuclei, but with a longer time, gives you larger grains. That's a thing that should make sense as the heat flows out on all sides of the mold. And the top will tend to have a sort of depression of sorts. That's a little exaggerated, but gives you a sense of what is going on there. So that's what he said. In order to get to your exact level, you might have to put in a lot more metal, especially because of how much metal is going to be consumed by creating the sprue. There's some other things about mold making and things, but we're not trying to learn everything about mold making. We just want to understand that these columnar areas are formed. And in this case, there may have been some more rapid air cooling. It's very common to have a shape a little bit more like this, where the longer grains will follow this general trajectory. So the longer grains will fill this region, the shorter grains will be here, and you can see typically different layers often if it was cast in this direction. So this one appears to have had some cooling that was fairly rapid up at the top, so more rapid air cooling, and the center is where all of the heat remained for the majority of the time. So that's what's going on here. So this is helpful to understand. The idea is the more fine equiexed grains that you have, the more control you're going to have over the properties. This is also an important thing in the era of so many people being wonderful little snowflakes. There's no such thing as a perfect crystal. So all crystals have imperfections, and we need to understand why is it that these are important. Many of these properties are going to be something that happens as a result of the imperfections, and that becomes very, very important. So if there were no imperfections in metals, it would take inordinate strength to be able to move them. You would have to have Thor with Mjolnir in order to do, in order to, you know, create a form in metal foil. Like, it would be utterly ridiculous. It would take tremendous energy. So this is something we've highlighted in some of the other videos that you guys got to see. So I'm hoping those are helpful. But there's a couple types and things that we need to understand about what's going on. So the first category is point defects. So these are vacancy, meaning atoms that are missing. There's interstitial, meaning atoms that are there that shouldn't be there, in air quotes. There's also substitutional atoms that have displaced other atoms or something that started as a vacancy, and an interstitial, another atom came in maybe in an interstitial way and diffused into that vacancy, became a substitutional. There's a lot of different ways that these can combine to work together. But we have missing, we have interstitial, meaning it's shoved its way in, and we have substitutional, meaning it's taken the place of what would be a parent atom. There are line defects called dislocations, and there are grain boundaries that are area defects. So let's take a look at some examples. Vacancy is the simplest example, where there's compressive stress and distortion of the planes all around in order to fill that vacuum, because nature abhors a vacuum. It wants to fill that vacancy with something. So all the neighboring, immediate neighboring atoms kind of get drawn into that vacancy, causing distortion on the planes. One of the kinds of examples of that carpet ripple demonstration, this is physically what that's doing at the atomic level, which is why that particular demonstration is absolutely brilliant. Since I'm all out of area rugs, I couldn't do that demonstration. I'm not real big on interior design, so it's fairly self-explanatory. The self-interstitials are distortions along this plane that have the similar kind of effect going the other direction. The interstitial, meaning it's an atom that's often of a different size. It can be of the same size, but it often will be of a different size. So a self-interstitial is the same size atom that's pushed its way into what may have been a vacancy, or may have just pushed its way into another plane, and so it creates a ripple going the opposite direction, where it's causing basically trying to create tensile stress so it's going in the opposite direction of a vacancy, and that's going to try and cause the ripple to propagate going again the same sorts of directions along those distorted planes. So there is an equilibrium number of these distortions. There's a couple constants and a lattice parameter that we use to kind of understand them. So we want to be mindful of the fact that it changes with temperature, again, because the temperature tells us about the kinetic energy of individual molecules and how all of that works. So the number of defects is this NV, number of potential defect sites is N, is E raised to the activation energy, divided by the Boltzmann constant times temperature. So the Boltzmann constant tells us something about the energy capacity in joules per atoms Kelvin, or electron volts per atom Kelvin, depending on which side of the equation you're looking at. So whether you're trying to understand the electrical activation energy for conduction or the thermal conductive energy for the temperature basis, those defects are going to change. So that gives you kind of some of a range of what's happening there. So, and each lattice site is a potential vacancy site. So when we're looking at this activation energy, you can get a QV estimation from an experiment. Again, this is a exponential energy relationship. So the number of defect, that concentration, if we plot this, that concentration goes up exponentially with temperature. So higher temperature, higher likelihood of defects, higher concentration of defects. This is fundamentally why when we melt metals, they become more easy to form into new shapes. This is the mathematical necessity behind that operation. As we increase that temperature, all of these things are more able to move within the systems, and they're able to do what's called defect propagation, which is what we'll learn about, at least a little bit. We'll learn about that later this week. But this gives you an idea. So plotting it on a log-log plot, there is a slope that is approximately proportional to minus QV over K. So you can estimate what QV is based on the defects that are being observed. So there's kind of a handy way to be able to get after it. So the equilibrium number of vacancies for 1 cubic meter of copper at 1000 C, given a couple parameters. So the density is 8.4 gram per cubic centimeter. The atomic mass for copper, 63.5 grams per mole, given a QV of 0.9 electron volt per atom. And using Avogadro's number, we plug in the temperature converted to Kelvin. We plug in our constant in electron volts, since we have a QV in electron volts, so that we keep units balanced, because the exponent should be unitless by the time we're done. And that gives us about 2.7 times 10 to the 4 in terms of what the ratio is for number of vacancies per number of available vacant sites. So 2.7 times 10 to the minus 4 is a fairly low ratio, but that tells us that there are quite a few vacancies, even in that cubic meter at 1000 degrees C. So I think this is effectively where we're going to pause for today. We'll come back to some more details on Friday, because I know a bunch of people are going to have to jump and run to next classes and all the things. Last note on this, for that 1 cubic meter, you multiply the density times that ratio to get A. So the number divided by the atomic mass times density times that volume, it gives us 8 times 10 to the 28th sites. That's what I mean by there's actually quite a few vacancies at 1000 C. This is part of the reason why copper is as malleable as it is at high temperature. It bends very readily. because of that high number of vacancies, as a for instance. So we'll learn a little bit more about why that is, because anything times 10 to the 28th means there's an awful lot of them. That's an awful lot more than we have people on Earth times many, 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 many times. If you squared the number of people on Earth a couple of times, you're still not quite at that order of magnitude. So just some things to keep in mind. So that ratio is approximately 2.7 times. So there's, times 10 to the 28 sites times 10 to the 25 vacancies with that ratio. So even though it may not seem like a very high ratio, there's a lot of defects to work with. So any questions from today? I know you probably still have questions on the test and things like that. I can't really give a lot of detailed answers at this point in time, but any questions otherwise? There were a couple messages that I did get to follow up on. So anything else that we need to cover before we close for today?